What are minimum phase systems in control engineering? Imagine trying to tune a musical instrument and getting the perfect sound without any delay or distortion. That's similar to what minimum phase systems do in control engineering. They are special types of systems that behave predictably and smoothly. These systems are used in signal processing and control systems to make sure signals are transmitted and processed without unexpected delays or instability. A minimum phase system is a linear time invariant system, which means its behavior doesn't change over time and it responds proportionally to inputs. The key is that both the system and its inverse are causal and stable. Causal means the system's output depends only on present and past inputs, not future ones. Stable means that the output doesn't grow without bound over time. In control engineering, the transfer function describes how input signals are transformed into outputs. For a system to be minimum phase, all the poles and zeros of its transfer function must be in the left half of the complex S-plane if it's a continuous time system, or inside the unit circle in the Z-plane if it's a discrete time system. Poles are points where the transfer function becomes infinite, and zeros are points where it becomes zero. If any zeros are in the right half-plane or outside the unit circle, the system is non-minimum phase. Why does this matter? Because the inverse of a minimum phase system is also stable and causal. This means you can reverse the system's effects without causing instability or non-causal behavior. Additionally, the phase response of a minimum phase system can be directly derived from its magnitude response. This is useful because, in many cases, it's easier to measure the magnitude of a system's response than its phase. The fact that phase can be inferred from magnitude helps in designing filters and controllers that work smoothly. Any causal linear time invariant system can be broken down into two parts, a minimum phase system and an all-pass system. The minimum phase part controls the amplitude response and introduces minimal delay. The all-pass part only adjusts the phase without changing the amplitude. This decomposition helps engineers understand and design systems with desired characteristics. In practical terms, minimum phase systems are preferred because they respond faster and more predictably. They tend to have better stability margins, which means they are less likely to become unstable when you make adjustments or add feedback. Simple stable filters with all poles and zeros inside the unit circle are examples of minimum phase systems. On the other hand, systems with zeros in the right half-plane or outside the unit circle, like certain delay elements, are non-minimum phase and can cause unexpected behavior. To sum up, from an electrical engineering point of view, minimum phase systems are stable, causal systems whose inverses are also stable and causal. Their zeros and poles are located in the stable region of the complex plane, ensuring predictable phase behavior. This makes them essential in designing control systems that are both stable and responsive, helping engineers create systems that work efficiently and reliably.